not, so you don't have to write a 20 page for sure, but some words about the principal element of command of NCNP that you have used. I need to have an explanation of the input file. So I need to have the input and the output file. But as you have seen, the output file contains the input one. So it's just if you send me your output file, it's nice. But in your report, I need an explanation of the input and the output file. So for the input file, you have to explain me the different element you write. So, for instance, this surface represent that thing, this surface represent that other things, and I choose to use macro bodies to define my geometry, or I prefer to use normal way to define geometry. So some explanation so I can understand your input file. In the case of the output file, I don't need to have explanation about all the statistic tests and so on. So just the result and the principal element, like the variance of the result, the variance of the variance, and the figure of merit. So these elements, these three elements, I said that they are the most important element to prove that your, how can I say, your run was okay. So I don't have to, so you have to say me, okay, the variance of the variance need to be high or need to be small, and okay, it's the case in my example, in my exercise, so it's nice. The figure of merit have to be stable during all the run, it's the case, and the variance of my, so the standard deviation of my my result is less than 10%, means that yes, the result is relevant, for instance. So I don't need you explain me all the lines of the output file. And as you know, you have to make a pulse aid distribution. So I need to have the pulse aid distribution. So when you complete your result, you will see that, so perhaps I will try to show you a result you are supposed to obtain. So let me look at, I think that I have something here. Okay. So let me share my screen with you. Okay, so do you see my screen now?
Yes.
Okay, so what you are looking for here is the result of the tally F8. So in that case, for instance, you see that the tally F8, there is a certain number of particles launched. It's a percent distribution, and it's tally for photon and electron, or just photon, whatever you want. And here you have the energy binning. So from 0 to, sorry, from 0 to here is, so normally it's 2.5, yes, you see, from 0 to 2.5. And this is, so the first column is the energy binning. The second column, the second column is the particles, the number of particles. In fact, no, because it's the number of particles normalized to 1. So means that it's the probability of finding this energy in the spectrum. So it's 10 to the minus 6, for instance, for the first bin, it's 6.42 and something, 10 to the minus 2. So it's for one launched particles. Okay, so it's normalized to one mean launch particles. Okay, and the last column here is the uncertainty, so the sigma, the standard deviation of the count number, and it is expressed in percent. Okay, is it clear? So for instance, if you I look at the second result, you have a bin between 1 and 6.1, 1 10 to the minus 4 MeV, up to 6.1 10 to the minus 4 MeV also. You have 1.41 10 to the minus 5 particles in that bin of energy normalized to 1, so it's for one mean particles launch in your problem, and the uncertainty of this result is 5%. So it's 0.05 mean 5%. Okay.
Okay. Question, please.
So yes.
The second column is like the emission rate.
It's a view of the count.
Okay.
So in fact, if you want to compare this value with a real value obtained during an experiment, for instance, you had to multiply this value by the total number of particles measured, I will say, launched, so emit by the sources during the time of experiment. So you have to multiply by the activity, by the branching ratio of the specific energy you want. By the sum of all the branching ratio of the isotopes. So for instance, if you take cobalt-60, so this, for instance, is the value for the measurement or the calculation of the cobalt-60. If I want to compare with an experiment, imagine you have a source of 10 kilobecquerel, for instance, and you measure it during 10 minutes. So in that kind of things, if you want to compare it with your real spectrum, you have to multiply each of these values, so each of these numbers for all the column, for for the second column, you have to multiply it by the activity, means 10 kilobecquerel, multiply by the total sum of gamma emitted for 1 becquerel, so means 2 in that case, because you have 2 different gamma emitted. And you have to multiply also by, so I said 10 minutes, so 6,000 seconds means the total number of time, the time you, during which you make the measurement. Okay? So it's a way to define the efficiency, finally. Okay? It's clear? But nevertheless, you don't need, if you just show me a graph on Excel or on MATLAB or whatever you want, a way to show a graph from the energy, so the number of count related to the energy, it's nice. So in your report, you need two graphs like that, one for the cobalt 60 point source and one other for the volumic source containing potassium chloride and so potassium 40. So I think that I will immediately send a mail with this information so all the students will have it. Okay, it's nice, or you need more?
It's okay. Please, I have another question, and
Yes, sure.
it's not only regarding Monte Carlo. I want to. What is the relationship between Monte Carlo and there's another software, Genie 2000?
Genie 2000. Genie 2000 is a software to perform measurement. So Genie 2000 will give you the real value of a real spectrum, finally. But in fact, you can compare. As I said, if you multiply the second column of the F8 calculation, if you multiply each value by the total number of particles launched during your experiment, you can compare the spectrum obtained by MCNP and the spectrum obtained in the real life. But you have to be careful because MCNP consider just energy deposition. So MCNP don't take into account the movement of the particles inside the detector, which leads to a certain, I would say, thickness of the peak. So, it increases the FWHM, so the full width half middle. So it means that if you really want to compare these two elements, you have to change your MCNP spectrum and add what we call a Gaussian broadening. So it's possible to simulate the enlargement of the peaks, so the thickness of the peak, I will say, using a special function that you can immediately put inside the input file. But it's not asked, so you don't have to do it, but just let me know that you can do it. And so in that case, you can compare nearly perfectly, I would say, the MCNP result and the real measurement result. But the two software are completely different. Genie is just, it's important also, so it's a way to show the real spectrum of some measurement. Okay?
All right, thank you.
You're welcome. So as I said, I will immediately write the mail so you have all the information about the deadline for the exercise.
I got a question regarding the results that we're going to retrieve. I assume that they should be the same, even though Monte Carlo is randomized. So we're expecting to see something specific?
Can you repeat the question? I think that, so you say that all the results obtained by MCNP are not the same.
Yeah, I believe that they should be the same, even if it's random.
Not exactly, because so there is a statistical part in the process. So means that the spectrum, so the result depend on the seed, so on the first value defined by the random number generator. So two different sequences having two different seeds can lead to slightly different results. Mainly if you have a low number of particle launch. So if you have, for instance, 10,000 particles, which is peanuts for that kind of program, and you make it 10 times, probably you will have slightly different results. Because the 10 times don't have the same seed, so the same initial random number. Okay?
Is the random walk always the same?
The random
walk.
Yes. So the first number is different, and since the first number is different, means that the first interaction could be different, and so it can influence all the interaction that occur after. Okay?
Yeah.
So if you take a very large number, so 10 to the power of 10 particles, for instance, it's exactly the same as you in the real life when you're making measurement. If you make 10 measurements of 10 seconds, you can have a very different result. But if you make only 2 measurements of 10,000 seconds, probably you will have very small difference between the two of the two measurements. In fact, you just have the standard deviation between the two. And in MCNP, finally, it's the same. If you use a very low number of particles, you will have a standard deviation which is quite high, and means that your calculation is not relevant. You cannot trust in. But if you use a large number of particles, yes, for sure, always regarding the standard deviation of your result, your two different results will probably be quite close, but it's not exactly the same.
Okay, that answers it. Thank you.
You're welcome.
Sorry, please, that means the more you have particle, better is the result. Hello.
So, sorry, I forgot to open my mic. So the problem is that if your geometry is really complex, and if the point of interest, for instance, your detector is very small, imagine a pinpoint ionization chamber, for instance, and it's placed at a certain distance of your source, it means that if you don't use any variance reduction, the vast majority of the particle you will launch from your source will not reach your detector. So it means that to have a statistical, a correct statistical result, you need to launch a very large number of particles from your source. In the other hand, if you try to solve a problem where the source is very close to the detector, and in the case of if the geometry is very simple, you don't need so much particle to obtain a statistically good result. And in that case, increasing the number of particles finally is not anymore needed. You waste time in running process that you don't need really. So the number of particles depends deeply of your input, of the geometry of your problem. So in MCNP4, the one you can access freely on the platform, the student platform, finally, the maximum number of particles that can be launched is 10 to the power of 9. In fact, why? Because, and the answer is within the slides of the mathematical part. In fact, depending on the type of random number generator you use, you have what we can call a sequence. So means that there is a certain number of random number that can be produced by your generator. And so if you exceed after a certain number generated, in fact, the system is back to the first situation. So means, sorry, I will put my camera also. I think it's better for you to see me perhaps a little bit. So here, what I want to say is that if you come back to the first situation, because you have explored all the possibility your generator can give. So it means that after a certain number of particle launch, you go again to the first situation. Means that in that case, the increasing the number of particles will not improve the quality of your result. So in MCNP 5 and the latest version, 6 and 6.1, you are able to change the random number generator. So you can choose between different possibilities, the one that will give you the best option to have the largest number of random number generated. But it's not possible, it's not allowed, unfortunately, in MCNP4. So in that case, the only you can use is a LGG, linear congruational generator. And the characteristic of this is written in the beginning of the output file. So you can see what are the parameters used for this generator and what is the seed. So what is the first random number generated. Okay?
Yes.
Okay. So don't hesitate to come back if you need.